Hi, my name is Doris, and I'm a third-year PhD student from the University of Illinois Urbana-Champaign. Today I'll be talking about our work on VisPilot, which is a tool that guides users towards interesting insights across the space of data subsets. And this is joint work that's done with my collaborators, Himel, Huizi, Hazem, Elmeleegy, and my advisor, Aditya, Parameswaran. Visual data exploration is a common first step in understanding multidimensional datasets. One common way to explore this kind of data is through an operation commonly known as drill downs. For example, when we look at the 2016 US election result, we can see that the percentage of votes for Clinton and Trump is comparable, with very few that voted for other candidates. Now, if we perform a drill down, essentially applying data filters to narrow the data that we're visualizing to only the selected subpopulation, in this case, African American voters, there's a dramatically higher percentage of votes for Clinton compared to the other candidates. So as we can see here, drill down is a common data operation that allows analysts to compare effects between different subpopulations. And detecting the changes in these effects enable analysts to identify patterns and trends, generate or verify hypotheses, and is ultimately what often leads to insight discovery. Drill down operations are often applied in sequence, one after the other, and we can think of the space of possible distributions as a lattice, where each path in the lattice corresponds to applying a series of drill downs. At the very top of this lattice, we have the overall distribution, aggregating across the entire data set. Horizontally across the first level of the lattice, we might be interested in looking at, let's say, the female vote distribution, or the distribution of voters in California, and so on. Going deeper in this lattice narrows down our data subpopulation even further through the conjunction of additional filter predicates. So for example, we can look at the vote distribution of females in California or white Americans above 65 years old. Notice that the number of nodes in this lattice grows exponentially with the number of attribute values in the dataset. And to reach a particular node in this lattice, there's also a large number of potential paths that could be taken. Given this huge space of visualization that one can explore in the lattice, it is often impossible for the analyst to keep track of all of these visualizations while conducting an analysis. It is also not clear where the interesting insights may lie. For example, many visualizations may simply not be very interesting to the analyst, or the analyst might miss out on potential insights that are hidden in the dataset. So in this talk, I will first present the challenges of manual drill down, as well as a new class of fallacy that we identify called the drill down fallacy. Then I'll describe the design objectives for building a system that addresses these challenges. Using these objectives, I'll describe VisPilot, which is an accelerated visual data exploration tool that guides analysts through the key insights in the dataset. Finally, I'll present some of our user study results that evaluates the effectiveness of the system. To illustrate the challenges associated with manual drill down, let's look at an example scenario of two campaign managers, Alice and Bob, who's looking at the 2016 US election dataset. They want to study how voting behaviors vary across different demographics. So to perform this task, Alice looks at bar charts of normalized percentage of votes for each candidate. She examines first the overall voting pattern, and then she drills down to the African American subpopulation. She notices how different the African American vote distribution looks compared to the overall, and she finds this to be very interesting. Now for Bob, he also starts from the overall, and then he drills down to the female vote distribution. He finds that the subpopulation resembles very closely with the overall distribution. So then he proceeds his analysis by drilling down, adding African American as an additional filter. For the African American female distribution, he finds a significant skew towards votes for Clinton compared to the other candidates, and he thinks that this is a very interesting finding. So how can Alice and Bob be looking at the same dataset but reach two very different conclusions? This is a classic example of what we call drill down fallacy in this paper. Here, Bob was unfortunately misled into thinking that the African American female visualization shows a particularly interesting trend. But in fact, this phenomena could simply be explained if he had seen the African American visualization that Alice saw. Attributing the wrong cause to an effect can lead to detrimental mistakes in decision making. In this case, the flawed insight may lead to the incorrect allocation of campaign funds. So to resolve these challenges, our goal was to develop a system that automatically selects a small set of visualizations to summarize the key distributions within a given dataset. First, we wanted to ensure safety by preventing the analyst from falling prey to the drill-down fallacy. This means that whenever we're looking at a visualization, we need to ensure that the proper parent reference is presented to the analyst to help them contextualize what they're seeing. To find these proper parent references, we want to select parents that minimizes the distance between the parent and the child distribution. This is based on the intuition that if a parent looks very similar to the child distribution, then the parent representing the more general cause pretty much explains the more specific case. Given that we now have the proper parent reference for each of our visualization, we need to identify the visualization that will actually convey something interesting. We define something as interesting if it's visually salient. In other words, if its distribution is maximally different from its proper parent reference. Combining these two objectives, we want to select the visualizations with maximal deviation from its closest parents. In other words, this is the parent with the minimal distance to its child. And the intuition behind this, the min-max form of this overall utility, is that a visualization is interesting if even its closest parent is unable to predict its behavior. Finally, since we cannot display all possible visualizations, we need to summarize the dataset by picking k visualizations that together have maximal utility, while enforcing that there is at least one proper parent reference available for context for each of our selected visualization. In our paper, we show that this problem is NP-hard, and we develop an approximation algorithm to solve this problem. Now I will show a brief demo of our system, VisPilot. Here we're looking at the police stop dataset, which contains historical records of police stops in Connecticut. We select the x-axis as the stop outcome and the y-axis as the percentage of police stops that led to this outcome. We asked VisPilot to first generate 5 visualizations for us to start with. From the top, overall, we can see that police stops most often leads to ticketing, shown as the green bar, followed by warnings, shown in red, and arrests, shown in orange. Going on to the next level, we find that there are 2 factors that lead to visualizations with relatively high arrest rates. And this looks quite different from the overall. So on the left, we can see that in general, when contraband or illegal items are found, then arrest rate is higher than average. But if we proceed onwards, we can see that the arrest rate is almost 0 if the driver's race is Asian. And surprisingly, the arrest rate is even higher for drivers 60 years and older. So now as we go down this rightmost path, we can see that visualizations for a stop duration of more than 30 minutes results in high ticketing and arrest rates. We want to learn more, so we asked VisPilot to generate 2 more visualization summaries centered around this visualization. So now if we look at additional breakdowns of this filter, the trend mostly show high ticketing and arrest rates, followed by low warning rates. And this resembles very closely to what we see in the parent distribution. And so what we see here implies that if a police stop lasts more than 30 minutes, the outcome would more or less be the same and is less subjected to other factors such as the driver's gender, race, or age. To evaluate the effectiveness of VisPilot for human analysts, we performed a user study with 18 participants who have prior experience with working with data. Across the 2 different datasets, each participants were assigned 2 out of the 3 different dashboards generated by the different conditions. The conditions included VisPilot, as well as 2 other baselines intended to simulate conventional approaches for multidimensional data analysis. Our first baseline was breadth-first search, and this baseline simulates a dashboard generated by a meticulous analyst who exhaustively inspects all visualizations or filter combinations from a top-down manner, starting from the overall and looking through all the 1 filter combinations at the first level and then to the 2 filter combinations and so on. Our second baseline is obtained through k-means clustering on all the data distributions in the dataset. K-means essentially groups together similarly looking distributions and therefore showcases k-diverse clusters of shape distributions that is present in the dataset. And for fairness of comparison, all of these 3 baselines has a budget of k equals to 10 visualizations to display to the user. Now, given an assigned dashboard, Participants were asked to complete a series of tasks to measure how useful are each dashboard in helping them accomplish these tasks. These tasks included a talk aloud labeling exercise, measuring the insights gained from individual displayed visualizations. A prediction task, where participants estimated the value of a data distribution after seeing a related visualization in the dashboard. And an attribute importance ranking task, designed to measure how well participants are able to assess the overall importance of attributes across the entire dataset. Our user study demonstrates that in general, VisPilot guides participants towards more informed decisions for retrieving interesting visualizations, predicting unseen visualizations, as well as judging the relative importance of attributes in the dataset, compared to our two other baselines. And in addition to improving task performance, VisPilot also led participants to make more comparisons against other visualizations in general, and against more informative references to help them contextualize what they're seeing. Study participants also find that VisPilot dashboards are more interpretable. In fact, some participants even thought that VisPilot dashboards were handpicked by a human. We found that the naturalness of the hierarchical layout in VisPilot led to more discovered insights. To conclude, in this talk, I presented the challenges of manual drill down, as well as how drill down fallacy can mislead analysts into attributing the wrong cause to an effect. I then described the min-max objective to ensure that each visualization is compared against a proper parent reference, and that the selected distribution is visually salient and interesting. Using these objectives, I demonstrated how VisPilot can guide analysts through the key insights in the police stop dataset. And finally, I presented some user study findings that compares the effectiveness of VisPilot against the two other baselines. In conclusion, VisPilot is an interactive visualization recommendation system that automatically selects a small set of informative and interesting visualizations to convey key distributions within the dataset. We hope that our work promotes future research in developing intelligent tools for assisting users in the process of visual data discovery. Thank you for listening, and I'm happy to take any questions.
We have time for some questions. Right. I'll start again. So this is really interesting work, and it's clearly a problem that's becoming more and more prevalent with sort of automated analysis tools coming in. So when you were talking about this top-down approach and how your algorithms there, made me wonder, can you tweak this algorithm, or can this also be used in sort of a bottom-up or recommendation engine sort of way? So let's say you take a tool like Tableau or Power BI or any of these normal Viz tools. I create a chart which has a filter applied on it, and I look at that, I see a skew, and I see one of the candidates having a really high value, and I make this inference that, oh, this is where I should allocate the budget. But based on your algorithm, for that chart, you could have figured out, hey, there are these other things. So for the female example that you gave, African-American females, it's just a general distribution for that class of citizens. So could you at that point use the same algorithm but recommend that as a potential chart that they should look at before making an inference?
So that's a great question. And I can show an example that was part of this, the police stop data set. So you could see here that we're actually using the same objective that we were using, that I introduced, the min-max objective, in sort of, if there's a particular visualization that you're interested in this case, the duration equals to 30 or more minutes visualization, then you can ask the algorithm to sort of expand on this node and show the additional visualizations underneath this tree and sort of expand that lattice. So going back to your Tableau example, you could imagine where a situation where the user has already selected specified a visualization of interest, and they can say, show me more, or show me something that's, underneath this visualization. And this tool could be used for that.
But are you thinking, does it have to be underneath? Because I'm just thinking, what if you're on one of these leaf nodes here on the left, and the one above is a better recommendation at that point? Could that be a case?
That could be the case, but it wouldn't be, I guess, stratified on the visualization that you would be interested in. So in that sense, you would show the overall sort of dashboard to help people contextualize the current visualization.
Okay. Any other questions? Yeah.
Are you able to put constraints in terms of like the minimum sample size of each graph. So like, for example, like you might filter so much that you end up having like 10 people in that population. Can you like have like minimum constraints for how many people you'd like? Because everything seems to be percentages.
Yeah, so that's a very good point. And inside our saliency, I talked about how we're picking the most interesting visualizations based on this deviation, right? If something is maximally different, then we want to pick these visualizations. There's actually a factor that I'm not showing here where we multiply the ratio of the subpopulation size and its parent in front of this as a coefficient to account for that. And in our current iteration of the prototype, we're also adding coloring based on the subpopulation size to indicate to the user that that the populations are actually getting smaller, and they can actually hover over each node to see the number of rows that are used to perform this aggregate.
Any other questions? If not, I can go with one more, and then we can stop with that just because I want to make sure everyone can even know. So you're talking about distributions as sort of the primary metric, or bar charts are probably one example of the best way to show that. But have you tried this for other types of charts and other metrics, be it correlations or more of those diagnostics related metrics, and then kind of how does your algorithm scale to that, and if not, then what are possible ways to extend to those?
Yeah, so this approach is generic in terms of when we have this d as the distance function, any of the conventional distance metrics like KL divergence, or currently we're using Euclidean or L1, L2, all of these work for the context, but we would really need to run a user study or evaluation study to see if that's actually something that's perceptually interesting to the users. And then generalizing across different chart types, we would also have to look at whether those objectives make sense to the users in terms of thinking about the deviations and stuff.
All right. That was the last talk. Thank you all for attending, and speakers are going to be here just in case you have more questions.